Let's take a look at another one. Let's take a look at example 5. Let's solve using the Laplace transform the second order linear ODE y double prime minus 3y prime plus 2y equals e to the negative 4t. We'll start as we did last time. We're going to begin by taking the Laplace transform of both sides of the equation. I'm going to save a little bit of writing. We know that the Laplace transform is linear, so we can simply take the Laplace transform of each term individually, factoring out constants as needed. It's equal to the Laplace transform of the right hand side, which is e to the negative 4t. Okay. Now comes the new stuff. Recall the Laplace transform of the second derivative. That's going to be s squared times y of s minus s times y of 0 minus s squared times y prime of 0. So that's the first part. Then this is going to be minus 3. Be careful. One of the things you have to be on the lookout for is when we expand the Laplace transform of y prime of s, that's going to give us multiple terms. Every single one of those terms needs to get multiplied by that factor negative 3. So I'm going to write a bracket for this. The Laplace transform of y prime, we know is s times y of s minus y of 0 plus 2 times the Laplace transform of y. Well, that's the thing that we simply call y of s. And this is equal to the Laplace transform of e to the negative 4t. That is simply 1 divided by s plus 4. We're now going to try to simplify the left-hand side. So we have s squared y of s. From our initial conditions, we know that y of 0 is 1. So it's going to be s times 1, which is s, minus y prime of 0 is 5. So this is minus 5 s squared. We can distribute this negative 3 in. Negative 3 s y of s. And then a negative 3, this is going to be ultimately a negative 1. Negative 3 times negative 1 will give us positive 3 plus 2 y of s is equal to 1 over s plus 4. From here, we want to keep all of our y of s terms on one side. So we have our s squared y of s minus 3 s y of s plus 2 y of s. And any of the non-y of s terms we're going to want to take to the other side. So I'm going to add s to both sides, add 5s squared to both sides, and then subtract 3 from both sides. Oops, and sorry, I made a mistake here. One mistake, sorry. These s's, the s's count down. There should have been no s here. Okay, so I say something looked a little bit funky in terms of what we had. My apologies. Quick rewrite here. So we have s squared minus s times 1 minus y prime of 0, which is 5, minus 3s y of s. Glad I caught it now. This was 1 we said, so negative 3 times negative 1 is plus 3 plus 2 y of s is equal to 1 divided by s plus 4. Now we'll try to group all of our y of s terms together. And now, what else we have here? We have this negative s term, and then a negative 5 and a positive 3 would give us a negative 2. This is equal to 1 divided by s plus 4. We can now go ahead and get rid of this stuff. We want to keep only the y of s terms on one side. So we have s squared minus s plus 2. And I'm going to make an additional step of factoring out that y of s. And this is going to be equal to 1 over s plus 4 plus s plus 2. We are now going to get the y of s by itself. So let's divide both sides by the s squared minus s plus 2. Divide by s squared minus s plus 2, s squared minus s plus 2. And maybe even before we do that, let's simplify this right-hand side. Let's get a single fraction here. So let's get a common denominator. The common denominator should be s plus 4, s plus 4. So let's do that. So I'll keep this for the moment as s squared minus s plus 2. I feel like I dropped a 3 somewhere. Shoot, hold on one second. Yeah, I'm sorry, this should be 3. I had it originally, and it fell out somewhere. But this should be s squared minus 3s plus 2 times y of s is equal to, on this right-hand side, we're going to get a common denominator of s plus 4. This numerator had a 1 with it, plus, if we multiply this out, we are going to get s squared plus 6s plus 8. So s squared minus 3s plus 2 times y of s is equal to s squared plus 6s plus 9, all divided by s plus 4. And now we'll divide everything by s squared minus 3s plus 2. Divide by s squared minus 3s plus 2. So we finally get that y of s is equal to s squared plus 6s plus 9, all divided by s plus 4 times s squared minus 3s plus 2. Before we try to go to the next step, which will be the partial fraction decomposition, we want to make sure that our denominator is factored completely. And it's partially factored. We have s plus 4, but this second part can be factored as s minus 1 times s minus 2. So we're now going to use partial fractions to expand this. This is one of the ones that is, again, going to be pretty easy for us because we have distinct linear factors in the denominator. So s squared plus 6s plus 9, all divided by s plus 4 times s minus 1 times s minus 2. This can be broken apart as a over s plus 4 plus b over s minus 1 plus c over s minus 2. We're going to get an equation that's going to make it easy to solve for a, b, and c. Let's clear fractions by multiplying both sides of the equation by that common denominator, s plus 4 times s minus 1 times s minus 2. On the left-hand side, we get s squared plus 6s plus 9 equals, when we begin to distribute it into this parentheses, for the first term, the s plus 4's cancel, until we get s minus 1 times s minus 2 in the second parenthesis, the s minus 1's cancel, and we get s plus 4 times s minus 2. And in the last parenthesis, the s minus 2's cancel, and so we get s plus 4 times s minus 1. If we make some convenient choices for s, for example, to get a, let s be equal to negative 4. If I plug it in, we're going to get negative 4 squared plus 6 times negative 4 plus 9 is equal to a times negative 4 minus 1 times negative 4 minus 2. That's going to be 16 minus 24 plus 9. That's going to be negative 8 plus 9, which is 1, equals, this is going to be negative 5 times negative 6, which is positive 30. So 1 is equal to 30a, which means that a is going to be 1 over 30. And actually, if we kind of go back, I believe this might have been one that we already looked at from before. But let's kind of go ahead and finish it up. I knew this looked familiar. Recall to find b, let s be equal to 1. We would get 1 squared plus 6 times 1 plus 9 would be equal to, if s is 1, then this cancels and the last term cancels. So we simply get b is going to be equal to 1 plus 4 times 1 minus 2. And this is going to be what? 16 equals negative 5b. So b equals negative 16 fifths. And then lastly, to solve for c, let s be equal to 2. If s is equal to 2, then we get 2 squared plus 6 times 2 plus 9 is equal to, if s is 2, then this term cancels, and we get c, which is going to be 2 plus 4 times 2 minus 1. That's 4 plus 12 is 16, plus 9 is 25, equals 6c. So c equals 25 sixths. So we've successfully completed our partial fraction decomposition. So our solution, y of t, which is going to be the inverse Laplace transform of y of s, is going to be the inverse Laplace transform of 1 over 30 divided by s plus 4 plus negative 16 fifths over s minus 1 plus 25 over 6 s minus 2. Again, the inverse Laplace transform is linear. So this is 1 over 30, the inverse Laplace transform of 1 over s plus 4 minus 16 fifths, the inverse Laplace transform of 1 over s minus 1 plus 25 sixths, the inverse Laplace transform of 1 over s minus 2. We can now go ahead and compute each one of those. They are all going to turn into exponential terms, but what we get is 1 over 30. This should be e to the negative 4t. This is going to be negative 16 over 5, e to the positive t, and then plus 25 over 6. This would be e to the positive 2t. And so that is our solution, y of t, by using inverse Laplace transform. Again, super awesome method, very convenient. The partial fractions might be a bit of an aggravation or annoying, but again, in terms of difficulty, in general, it is significantly much harder to solve just general differential equations than it would be to do partial fractions or some basic algebraic style techniques.